Right, so last week we did use the command margins plot. Once you fit your ANOVA model, you can estimate your means using margins and then follow that up with margins plot, and it creates a nice figure that's already formatted for you. Right, so we run this first command, margins pints hash sex. Right, this will give us all of the cell means. And when you run margins plot, it gives us a nice figure. And this is the one that we looked at last week. For this example, we have the vertical axis representing the mean attractiveness ratings. On the horizontal axis, we have 0 pints, 2 pints, and 4 pints. And then finally, the lines represent male and female attractiveness ratings. Now, this example is great because I think it really drives home that interaction. Remember that if a figure is, if the lines are not parallel on a figure like this, there's probably an interaction. And when they cross, as they do here, then an interaction is definitely present. And it also helps to best demonstrate the differences of differences. Right, so we can see that males and females don't differ too much after having 0 pints. They don't differ too much after 2 pints. However, at 4 pints, it's very clear that men are dipping significantly after consuming 4 pints of beer. So, just by visualizing this really quickly, we can see that men at 4 pints are probably driving that interaction, considering that females, the red horizontal line, really isn't changing that much. The slope doesn't change between 0, 2, and 4 pints significantly. And same with men at 0 and 2 pints. There isn't much change here, and it's pretty close to how females are rating attractiveness. But again, at 4 pints, there's that major dip that is probably driving or influencing the significant interaction. Now, you might want to organize your independent variables a little differently on a plot like this. Say, for example, you wanted male and female. Uh, you wanted the variable sex to be on the vertical axis, and you wanted pints to be represented by lines. How should you go about doing that? Right. So let's demonstrate that now. Right. To do this, we're going to use the same series of commands here. However, keep in mind you have to refit the ANOVA model. This margins plot command is what's considered a post estimation command, which means it will run this command on the previous model that you fit. However, our last model that we ran already has margins associated with it. So all we need to do is rerun the same exact command here, ANOVA, our dependent variable attract, and the two independent variables sex and pints. Recall from last week that this double hash here is telling Stata that we want to do both the main effects of our two independent variables, sex and pints, as well as the interaction. That's really important to remember to include. Now that we've refit the model in Stata, we can run the next series of commands here. Now, you'll notice that these are pretty much identical, these two commands. The one above, we had pints hash sex. In this case, we're going to write out sex hash pints. And in doing so, this will mean that sex is going to be on the vertical axis, while pints will be represented by the lines. So let's see what different type of information this type of plot can give us. All right, again, on the vertical axis, we have attractiveness ratings. This time we have males and females represented on the horizontal axis, and the blue lines refer to 0 pints, red is 2 pints, and green is 4 pints of alcohol. Now, the actual means that this plot represents haven't changed at all, but it looks quite different visually. Again, that's just because we're switching what's represented on the x-axis and what's represented by the lines here. And this figure again really drives home that interaction being the difference of differences, right? So again, for males at 4 pints, we can see that attractiveness ratings is quite a bit lower compared to at both 0 and 2 pints. In fact, it appears that zero males who had 0 and 2 pints are pretty much exactly equal in how they rate attractiveness. So, this difference between those groups here is much more extreme than the difference for females. And again, it doesn't actually appear that women are changing in their attractiveness ratings after 0, 2, or 4 pints of alcohol. Now, in this figure, even though the lines aren't crossing as they did before, we still very clearly have an interaction because the lines themselves are not parallel. Right? So when you look at a figure like this, you don't just consider if the lines are crossing to note if there's an interaction. Again, as long as they're not parallel, if the lines continued, if the lines continued on, they would certainly cross. Right? So the cross doesn't actually have to happen on the graph. Now, at the end of the day, it doesn't really matter which method you choose to present your results, just what makes most theoretical sense when it comes to your interpretation. So either way, it would be perfectly acceptable to present either format. Though I do prefer to have, if there's a discrepancy in the number of levels between your independent variables, I do like to have the the variable with more levels represented on the x-axis and the one with fewer levels represented as the lines. That's just my preference, especially when you get more and more levels, it becomes quite messy. So for me, I would probably prefer to have 0, 2, and 4 pints on the x-axis. But again, you still get the same information at the end of the day. Now you can also represent these data using bar graphs. Before we can generate these bar graphs, we have an additional step. In fact, we need to generate another new variable. Now, remember last week when we wanted to assess the assumption of homogeneity of variance, we created a new variable called cell. And this variable was essentially a numeric identifier for each level of each of the independent variables. We're doing something slightly different here. However, this new variable is simply going to be the cell means. Okay, so the mean attractiveness ratings for males at 0, 2, and 4, as well as females at 0, 2, and 4. And those are the values that we'll use to populate the bar graph. This command is called predict, and it is a post-estimation command, which means you have to refit the ANOVA model, or else you'll get an error if you try to run the command as is. Right, so I've already done that here. We have the source table. So now when I run this command, you'll see a new variable pop up in our variable viewer. Right, so we have the fitted values or the mean values, and the variable is called y hat. When we go to the data viewer window, we can see this new variable, again named y hat, includes the mean attractiveness ratings for males at 0 pints, 2 pints, and 4 pints, and so forth. Right, so now we can actually generate this new bar graph. The command's quite simple. It's graph bar, right, and then the variable y hat, and we want this over both sex and pints. Right, so let's run this command. Just like with the other figures before, the y-axis is the mean attractiveness rating, and we have pints on the x-axis, so 0, 2, and 4 pints. And the bars are represented by males in blue and females in red. Now, we're not really getting any new information here since we've already visualized the figure in two different ways previously, but this really does drive home how similar males and females are in attractiveness ratings after 0 and 2 pints, and then how extreme that difference is at 4 pints. So again, this is really driving home what we're probably going to see with the interaction. And just like before, we can generate the table, rather the bar graph, using the opposite method. So we can have males and females on the horizontal axis and pints represented by the bars. To do this, it's quite simple. Again, we just need to switch the order. Right, this time the command is graph bar, again, y hat. This time, pints will go first and sex will go second. Now, it's a little confusing because it was the opposite order using the margins plot command. So when you're using the margins plot command, whatever goes first will go on the x-axis, and whatever is second will be represented by lines. We see the opposite effect here. Whatever is first will be um, on the x-axis. Sorry, whatever is first will be represented by bars, and whatever is second will be represented on the or on the x-axis. All right, so this time pints will be represented by bars and sex will be represented on the axes. Everything else, though, is exactly the same. All right, so this time the blue bar is 0 pints, red bar is 2 pints, and green is 4 pints for males and females. Whereas the graph beforehand really highlighted the difference between males and females at 4 pints. What we see here is how similar females are overall at 0, 2, and 4 pints, while males really do seem to drop off after 4 pints of alcohol. So again, just to reiterate, we're not getting new information here. It's just all about what presentation tells the best story. What's going to be the most useful way for the reader to come to the right conclusion based on the story that you're telling, based on the data that you're presenting. So maybe it's the case that you want to present your results to specifically demonstrate how males differ between 0, 2, and 4 pints of alcohol. In that case, this would be the best way to present the bar graph. On the other hand, if you want to highlight how males and females differ at 4 pints specifically, then you'll want to use the other method. Again, it really depends on your hypotheses, your research questions, as well as what makes most theoretical sense. Now that we've visualized the data in every way possible, let's go ahead and do the simple effects in every way possible as well.